Hello, hi Bruno. Can you
Hello.
hear me?
Yes, yes.
Okay, I can also hear you.
Okay, very good. Yeah.
I was just checking.
Yeah, me too. So if I use Firefox, then for some reason whiteboard doesn't work. But in Google Chrome it works. But it's like an application that doesn't depend on the browser. So something strange is happening. Yeah, so what I will explain today, I have written it, but unfortunately I changed everything in the weekend and my text still has small mistakes. So I can share it in the chat while we're waiting, but I'm not sure if it, so I hope it's not too bad. Oh, no, screen, something else.
Kind of strange warning. Anyone with access to the recording may view or share it with other. It's kind of
Scary.
strange idea of access which doesn't allow you to view the recording. Okay, so did you put something, some link somewhere?
Yeah, so the file, I put a file, it's the writing, but I mean, it contains all the ideas, but there are still small errors because I was changing all the time things. So I should read a few more times. And then I will post it on the archive.
So, but you put it where? No, you're
In the chat of Zoom. So maybe if,
the chat of Zoom doesn't show anything.
yeah, because I will share it again because you probably just too
the
late.
board link.
I will use whiteboard. I didn't have time to learn something nicer.
So you will use Zoom whiteboard or what?
Yeah, Zoom whiteboard. So you should see it already, the Zoom whiteboard.
Yes.
Yeah. Okay. So Sasha, I shared the file in the chat, but I need to press enter. Sorry. Yeah. Okay.
Okay.
Yeah, I think after it's 2 years after COVID, I already forgot everything.
Bruno, so how long do you plan to talk? Because I'm not usually attending this seminar. I think it's the first time I'm.
Yeah, the idea is that it's finished at 8 o'clock. And
So in 1 hour and a half.
yeah, sorry, yeah, 1 hour and a half. Yeah, Moscow time, yeah. Let's check who else is here. So shall we start or wait a bit?
No, I guess we can start slowly.
Yeah. Okay. So so what's the goal of what happened? So Alexei Milovanov and Bruno Lov showed me paper about key agreement. And the goal of the paper is to have some characterization of conjecture key agreement exists in a bit more combinatorial flavor using Kolmogorov complexity. And so the paper is by Bauwens, Pass, Mazor, and in 2023. And the paper is very long, it's 40 pages, and they make characterization of one-way function and key agreement using a single notion of Kolmogorov complexity. And so Bruno Love told me that the characterization of one-way functions he doesn't find interesting, but for key agreement, he said it's very interesting, and he wanted to understand the proof. Unfortunately, the proof, it's like 30 pages. It spans a lot of pages and is very complicated with not too many lemmas inside. And so I read the paper, and then I understood that what they're doing is similar to construction of dispersers and shortlist paper. So they construct certain hash functions implicitly, which I know about. So it was familiar for me to read. But then I rewrote the proof using the shortlist result, and then I understood that it was not needed at all. Some basic hashing was enough. And so I think that after all the simplification, and then this weekend I found a way to even split the proof of the harder part of the theorem in two blocks. And that's why I was struggling to have a nicely written version that I shared in the chat, so which still has a lot of typos. So tomorrow I will read it and post it on the archive. I mean, that's the plan. Okay, and so now as kind of a proof that the proof is easier, or demonstration, I want to explain it in current
To
seminar.
start explaining the previous proof.
No,
Hopefully.
that's too difficult. I cannot remember the previous. I completely forgotten everything. So,
Yeah.
but I remember my own proof. So yeah.
Good.
So but first let us say what is key agreement. And so then we say what is the conjecture, then I will say what's the theorem, and then we prove the theorem. So so there are two players, Alice and Bob, and they exchange messages, and so they generate a transcript. So there are any number of rounds, and after some time, they stop exchanging messages, and Alice generates some private key, and Bob generates hopefully the same key. And the idea is that Eve, who listens to the communication on the public channel, who knows pi, cannot compute what is x. So what is a clue here? That E is time bounded. So if E didn't have any limitation on computational power, then it should not be too difficult to prove that it's impossible. Okay.
So we don't have any input here.
Well, I will. They have a number n as input that determines the probability of agreement and security. So I can give a formal. Let's give a formal definition. Just a highlight.
And
so
they
then
they are just they are randomized algorithm, I guess.
yeah, randomized algorithms. So let's just go to formal definition of protocol. So protocol, it will be. Okay, and
A
so
pair of probabilistic machine for Alice and Bob,
yeah,
which get input n, and then provide some exchange, and each of them makes some output x.
yeah.
And the first condition, I guess, will be that with high probability, s is an n-bit string, and with high probability, it is the same from A and B.
Yeah. So we will just speak about distributions of messages and two secret keys. That's all we need, but we assume that there exist algorithms A, B, to generate a protocol, and then to generate a private key, Ka and Kb. So they're probabilistic polytime algorithms.
With high
So,
probability, the keys are the same.
yeah. So we say that the protocol. So do I need to explain more? So there is a function A. It receives. So initially pi is empty. So let us fix everything so that
So
it's
you want to explain what now?
how formal definition. So the protocol it consists of 4 functions. So and then a dial.
A protocol is just an algorithm which sends and receives messages according to some algorithm.
Yeah.
No,
Yeah.
why should we need to say something more specific?
I don't know. So maybe some people want to know how it works. So what happens is that there exists some pi, and then Alice sends a reply. So it depends a string I. So we need to say I, is it a bit or a string? So in our case, it will be a string. So, but if you want it, it can be a single bit. So the reply, they in turn send a bit, and then they know how to finish. It is if one of them sends the empty string.
Okay, why do we need all this detail? It's important for a SQL or not? It's frightening that you do this because it seems that maybe you will use this detail somehow.
Well, at some point, they need to stop and so on. There will be questions how it's related to online complexity. So, okay, it's not so important, but just I want to be
This is just a
safe.
standard protocol, like in communication complexity or whatever. Just
Yeah,
nothing
yeah,
special.
yeah. I agree. Okay, and so then we should say what is agreement. So protocol has agreement. Agreement alpha of n. So alpha of n. So when I check everything was working, but now again not. So agreement alpha n if probability that x equals y is bigger than alpha of n.
So alpha of is assumed to be close to 1.
Yeah, indeed, yeah. And then has security epsilon n. If so for every probabilistic polynomial time algorithm E, and then for all but finitely many n, so probability that E of
Watching
n,
the exchange can
yeah,
reconstruct this key.
should be smaller than epsilon n.
Sorry, when the input length is n, on input n, the keys has to be of length n.
No,
Yeah,
the
I
key
think
can
there.
be any length, and the protocol can also be any length.
The key can be any length. Okay.
Yeah.
So it can be of length
That's
1.
a security parameter.
Yeah.
Yeah, it can be of length 1, but then we cannot have good
Yeah,
security.
I don't
security
hear.
indeed.
No, it can be of length 1, but then we cannot have good security properties.
Say that if it's also, if we can make 1 bit, then you can repeat it.
No,
Okay,
you cannot
I
make
can't hear,
1
but
bit
I
because
guess I understood.
you can just guess. The eavesdropper can guess the key then with probability 1/2.
Yeah.
Okay.
Yeah, by the way, before we go further, is there some obvious way to make amplification of alpha? So imagine we have alpha, I don't know, 99%. Can we make alpha 999, 0.999 or not?
Yes. So by exchanging hash code. So what we do is we exchange a hash code, and if it's different, then we repeat the protocol. So, but it's bad because for security. So if you do this, you decrease security because you reveal information about X.
But you don't require that if does not get any information about X. What you require is only that if cannot reconstruct X completely.
Yeah, exactly. But if you reveal some information about X, then it might become easier to reconstruct X. So that if you show exchange a logarithmic number of hash bits, then the security decreases by polynomial. But then you can again increase the security by repeating the message. So, but now let us define key agreement, because key agreement means negligible security. So if
now you
must
state
fail.
the conjecture.
Yeah. So
key agreement conjecture, what it is.
Well, there is a definition, like key agreement protocol. So I just say any protocol is just a triple, a set of functions, and a key agreement protocol is polytime computable protocol. Oh, there is some echo.
I guess someone should switch off the sound.
So here, I mean polynomial and n, so there is the input n. That is 1 over n to the power, that for all c is 1 to the power n to the power c secure, and has agreement uh, 1 minus n to the power minus c. So this is, and now the conjecture is key agreement exists, or the question.
Yeah, but the protocol depends on C or not, or
No. So for all C, it must be 1 over n to the power c secure, and have agreement 1 minus n to the power c.
Yeah, but then you should say in the agreement that this is true also for sufficiently large n. Otherwise, you cannot have this.
Yeah, for all, but sorry, agreement for all, but infinitely many n. Yes, sorry. For all, but finitely many n. Okay, so now we have
And now you said maybe implicitly that this is kind of a robust definition. So, for example, I can guess from what you said that if we have such a protocol for C equals, I don't know, 2,
yes,
then we have also key agreement protocol in this stronger sense, or not?
yes. So it's enough to have, and even better. So we can have even agreement, very small, polynomially small, and security polynomially, like arbitrarily close. Let's say polynomially small, conditional on having agreement. So just we are only polynomially small, conditional to agreement, even if agreement is polynomially small, and still we can build. Still, people can build a key agreement protocol.
Yeah.
So
this definition is robust. I don't know whether it makes sense to discuss this robustness before other things, or we just can postpone it until we know the main result.
So I can say a general theorem. There are simple observations. So we can boost agreement, as I already said, by exchanging hash bits. And we can boost security by repeating the strings. But it's not completely obvious that repeating helps against polynomial time verifiers. So we need to think about conditional distributions. And later we will use Hohenstein theorem that gives quite powerful boosting. So actually quite soon we will need it. So let me write Hohenstein theorem.
No, so now we're trying to discuss this amplification or what?
Yeah, amplification we discuss now.
And so we're assumed to understand the details. Okay, let's try.
No, to prove the theorem is too difficult by Hohenstein. If you want, we can have easy boosting properties. We discussed these. I forgot to prepare, but maybe it works. Okay, so Hohenstein theorem says that it's actually a weaker version of what he proved, but this will be enough. So this says that if we have just any alpha, sorry, let's say any beta and alpha, so that every, so if every
Beta and alpha are numbers. Or functions.
Real numbers.
Yeah.
So if every protocol with 1 minus n to the power minus alpha agreement is not 1 minus n to the power beta secure, then key agreement does not exist. So if we can just, if a protocol with quite weak agreement
doesn't exist, then stronger agreement, of course, doesn't exist. You mean something else, I guess.
Yeah, I mean something. Oh my God.
No, maybe we don't need to discuss the simplification now. Just I asked, but this is not. If you say that we will.
Yeah, we will
don't need to
anyway,
understand the details now. It's okay. If you want to explain something else, it's. I don't want to distract you.
Okay, so sorry, I said I was saying it in the wrong direction. Okay, but yeah, let's indeed first go to the.
Let's keep it for a while and then return when necessary.
Good. Let's erase this. Now our plan is to give characterization. So for this, I need some definitions. It's a notion of interactive Kolmogorov complexity.
Okay.
And also, I will say that the problem regarding interactive Kolmogorov complexity is in IOBPP. So let's do the easy job first and say when a promise problem is in IOBPP. So promise problem will be consist of two sets, a yes set and a no set. So yes set, our algorithms should say yes, no set should say no. And we say that it is in IOBPP. If there exists probabilistic algorithm, again, probabilistic polytime algorithm, so that if and infinitely many n, so that if W has length n and is in Y, then algorithm should say not in n. So it's a promise problem. If input is not in Y or not in n, we don't care what the algorithms say. But for infinitely many n, so we will use binary strings intersect Y. Then with high probability, algorithm W should output not an n, outside n.
Just should output y. Why you say in a strange thing? Output yes.
Because it's a promise problem. So
you can say algorithm says yes. Why you need to name this complicated algorithm in a strange way?
Just I want to handle the case if it's neither, then it should not lie. So we want an algorithm that's never lie because I will use contrapositive, and so we should be careful. Otherwise,
it cannot make error even with a small probability, or what?
Yeah, with probability 2/3. So I just need to move my screen a little bit to the right. So it should say outside n. With probability 2/3. And then if W the same for n bit in n, then probability of saying outside y should be 2/3. And so note what is a contrapositive. So there are two requirements and we will use contrapositive. That means if algorithm, in the first requirement, if algorithm says outside yes, with probability more than 1/3, then it should indeed be outside yes. It's contrapositive of first statement and similar for second one.
Sorry, what is it? No, that's completely strange for me. First of all, you have two answers. You can use any you can call yes or no, or you can use any two different strings. But
yeah,
okay, if you want
so
this
but
answer,
this is
why not?
equivalent to saying that if probability of outside n is bigger than 1/3, it's bigger than 1/3, then W should not be in Y. Outside, sorry, I'm mistaken. If probability of outside n is bigger than 1/3, then the, sorry, it was correct.
I think it's just a PPP condition, which are well accustomed to. You can put it in a rather strange way, but it's still the same. We just should produce correct answer if we are in n or y with probability 2/3, and we have no obligation if the input is neither in n nor in y. That's what we.
Yeah, but I want now for once draw attention about the contrapositive.
Okay, just say it again. What you want to do.
So if probability outside y is bigger than 1/3, then W should be outside y.
Yeah, okay.
So, and of course the same for the other things. It's just for the proof, of course, for the statement, it doesn't matter. Okay, and now I need to say what is interactive complexity, and then we can say the main theorem.
Yeah.
So there are two machines, U and V, and interactive complexity of a protocol and X is just the minimal length. So minimal length of programs by Alice and Bob to generate such that they generate protocol pi, and each of them compute string X. So it's minimal.
It's not clear. Pi is what? Say it again.
Pi is a transcript. So A and
Not
so
protocol,
A and B are two a transcript. So A and B are two programs for Alice and Bob, and then these programs should generate transcript pi. And then we use a different machine, a given again transcript and program A, and then Alice should have X, and Bob should have also string X. So let me write it like this. So when we let A communicate, so we use U machine to generate replies, and Bob also uses machine U to generate. We can use different machines, it doesn't matter. And this should generate the transcript pi, but also Alice can use a different machine V and the generated transcript to get X, and same for Bob. X, and this should be B.
But it's very strange. So machines U and V, do they have any randomness?
No.
No.
So here are deterministic machines, and A and B, that's similar to Kolmogorov complexity. I think everyone here knows Kolmogorov complexity. So this is a variant.
Yes, but explain what the variant is.
So variant is that programs are used to generate transcripts, as in the communication complexity. So it's a bit of the reason why I want to do the detail. So how does it work? So pi initially is empty string. And
pi is just a sequence of messages between Alice and Bob, or not?
Yeah, but you want me to say clearly how pi is constructed using programs A and B. So initially pi is
No,
empty.
I no. What I'm saying is quite strange. Why? So usually in our previous setting, the machines for Alice and Bob also use some private information to generate X. Otherwise,
yeah, but the programs are private, A and B.
But the program V is somehow also is usable both from Alice and Bob. What is then the difference?
But U and V are fixed machines, and the programs are different.
Sasha, I think I get the definition.
Yeah, just explain.
I can explain you. We have two machines, A and V.
Yeah.
First, they chat between each other. Then, at some moment, they decide that it's enough. The chat is finished, and every machine outputs a string, and that string should be the same. And A and B are just private inputs of those machines, and that's it. And the interactive complexity of X is the minimal length, the minimal total length of these private programs, and that's. For instance, it is at most the normal complexity, because one machine can just generate the text and send it to the other machine. The other machine outputs X, and we do not need the second private input. But here, in this variety, somehow this program is divided into parts. One part is given to Alice, the other part is given to Bob.
No, I understand that there is a notion, more or less standard notion, of interactive complexity, which we have just a sequence of messages, and we need a program, two programs, which compute are enough for Alice and Bob, that are enough to maintain this dialogue. So
I haven't understood the statement that this complexity is at most the normal complexity of pi and X.
So let me start from the beginning. So imagine we have a sequence of strings, which is called protocol pi, but it's just a sequence of strings. And let's consider, we can look for the complexity of the tasks produced the each strings number 1, 3, 5, 7, and so on, given the previous strings. So provide the Alice, to simulate the Alice part of the dialogue. And it's program A. And also there is a program B, is enough to produce the other part of the dialogue. So this
Yeah,
is
but it's not the same.
This
because
but wait a bit. This is kind of interactive complexity of two things. And here there is something different. First of all, we are looking only on the sum of the lengths of A and B. And second, there is some special attention to some X. So you should explain more what is the difference, what is the common things and what are different.
Yeah, okay, so I will just say the detailed definition and then everything should be clear. So first, so how the programs work. They construct a string pi and X as follows. So first pi is the empty string. Then to pi, Alice will concatenate the value of the program on A with the empty string as input. Then Bob will concatenate his part, and then they repeat until one of them sends the empty string. So Alice reads the transcript so far and may concatenate
if we look
something.
only at that moment, is it the same that this online complexity or not?
No, because it's not specified how the pi is broken into pieces.
It's not specified how pi is broken into pieces?
Yes, we don't care about this. What we do care about is that, sorry, I made a mistake. Again, that should be
Sasha,
you.
I guess if we just neglect this small problem about breaking into pieces and X is empty, assume that X is empty, then this is the same as interactive complexity. So first Alice computes some part of the output, then Bob computes the second part based on Alice's message, and so on.
Well, I don't understand this statement. That this definition is conditional on U and V. So is this
No,
the same? The statement is
just
the same for every U and V?
No, U and V are kind of universal machine later. So it's like usually we consider the optimal U and V.
So I guess there will be a statement that there exists U and V almost optimal.
Yeah.
Yeah, but I mean, because I was confused that this statement wasn't made, and then somebody was telling that it's the same or not the same, so it was completely confused.
Yeah. Okay. So
why do we need U and V?
Usually we define complexity with respect to some universal machine and then prove that the complexity doesn't depend on the choice of the machine. So here we do the same thing in the same way without. So this is kind of normal thing. We usually do things.
Yeah. And so here I've written a property. So interactive complexity of pi and X is bounded by complexity of pi and
but
2 times.
Wait a bit. So it's really important that we don't separate X into sequence of messages and take concatenation. This is it's a really important thing, or not?
Yeah. So X is very different from pi.
No, not X. Sorry. So first of you don't consider pi not as a sequence of messages as usual in communication complexity, but as a sequence of bits.
Of string, well, concatenated strings.
So actually pi is just a sequence of bits without specification. Yeah. So this is really important.
In the proof, it's not important. If you want to change the definition, the proof will still work.
So it's not that important. And then you should explain the role of X. Just.
Там внизу на созвоне я слушаю семинарчик на такой.
Alexander, you should switch off the microphone.
Okay. So So now say something more about X. What is the idea? Why? What should you?
Yeah. So now once we fix pi, Alice and Bob need both to compute X, but they cannot compute. So if pi is the empty string, then this will be twice the Kolmogorov complexity of X.
But before you say the statement, just what you say that additionally you need that the programs for after this exchange, the programs
the programs
can compute.
Yeah, need to compute X. So we need that they compute the same string X. So we need X equal to Y in this explanation.
So we have kind of online complexity with additional thing X, which should be as an output of both machines.
Yeah.
And I guess in this formula, we can add the condition. So the complexity of pi plus 2 times the conditional complexity of x given pi. Isn't it?
Yeah, right.
Yeah, after they have pi and they use some information to produce X.
Yeah.
No, actually, there could be also some logarithm if we are of n, if we need. It's not.
Yeah, sorry. Yeah, you're
clear.
right. Yeah, we need. Yeah.
Yeah, but
Length of pi.
no, it's so we have this online complexity, and plus this additional thing.
Yeah. And now we need the time-bounded version of this. So T will be a mapping from natural numbers to natural numbers.
Again, you consider, instead of, why don't you consider just a number as a bound? Why you need such a strange thing? Just because all other people do this, or there is some more specificity?
Yeah. All other people do this, but it's reasonable because the n will always be some function of n.
We can put, if we define it with a number argument, nothing prevents us from substituting this argument.
Yeah, but then all the time I need to write the argument here.
No, then you will give additional
cumbersome.
quantifier. We will have additional quantifier on T, as usually it will create, somewhere it will create problems. But okay, if you want to do the same error as all others, you can do this, but obviously it should be not like this. Okay.
Yeah. So and then we require that the sum of all runtimes is at most order T of n. It's ordered T of. Okay, sorry. Let's say T of n. Otherwise, it's a mess. It doesn't make sense. So let me write this T of. I mean length of pi. So we use pi length of pi as parameter. Okay, so now we know all definitions, and now we will define promise problem and say that it's an IOBPP if and only if key agreement exists. So I will move the screen down now. So I think you all have to do this.
No, we don't have any way of watching your screen except for using Zoom. So
yeah.
It's happening.
But if I move it down, you also have to move down, or you see where I write.
We see what you are.
Okay, you see exactly the same screen. Okay. Yeah.
No, actually there is an option not to follow your screen here.
Right.
Okay.
Sorry.
Yeah. So now I will define a yes set, and it depends on a time bound T and a number C. And so it is all the pairs by X, for which that interactive complexity is close to the complexity of protocol. So interactive complexity of pi X is bounded by complexity of protocol plus C log and then the length of the protocol. And then I define the no set, and this is the complexity of all pairs pi X, for which complexity of pi X, but now the standard complexity of the pair is bigger than complexity of protocol plus E times log length of pi. And now we say that under small conditions on the parameter. So this problem, it has three parameters, C, E, and T. So let us first have, so we will now think about the promise problem of distinguishing these two sets. And so a simple observation, if we make C smaller and T smaller, then the problem becomes easier. So problem depends on C, E, and T. So if C and E become smaller, the problem is easier. If E becomes larger, the problem is also easier. Why? Because the sets become smaller.
No. If E becomes smaller, the problem doesn't become easier.
If E gets larger,
so
E
C
gets
can
larger.
be decreased and E can be increased, then we get the smaller sets.
Yeah. Okay. So now the question, are the sets disjoint? So if the pi is large, are the sets disjoint? And so answer is that if E is strictly bigger than C, then the sets are disjoint for large enough n. So on CT intersect.
So n is what?
For protocols that are long enough.
So do we have some assumption about the connection of the length of protocol and length of a relation between length of pi and length of x?
So I will assume that x is shorter than pi.
X is shorter than pi.
Yeah. So, well, in the definition of IOBPP, we need to be careful. So this is a very annoying definition of IOBPP. I forgot to discuss this because, so here we have it back. Because if we do minor, minor changes in W that affect the length can destroy the property or make the property trivial. So we have to be careful with the definition of IOBPP for pairs. So note that the requirement is that there exist infinitely many n. So this is the most ugly point. It is the sensitivity to simple formatting of pairs. And so in the paper, it's solved by requiring that pi is of equal length of x. And so n will then be the length of those pairs. But then it's a bit annoying because all the time you have to say construct x like this and path to length of pi and vice versa. So it is nicer. So let us now define it for pairs in a way that doesn't bother us. Yeah, so let us just say that, let us require that pi has length n and x is shorter than n. Then we don't have this problem. So let me write it carefully. So there exist infinitely many n, such that if length of pi equal to n, and length of x is shorter than n, then and pi x is in y, then this condition holds. And the same for...
So you changing the definitions of IOBPP or what?
So I didn't say how I define it for pairs of strings. I just said it for sets of strings. So if the set consists of pairs of strings, then we cannot just say use any coding that doesn't blow up the size too much. Because it depends on the coding we choose of the pair.
Okay, but so you define encoding now, but you don't change it.
No, I don't define encoding.
I think we can skip this technicality. Forget about this. Let's proceed.
Okay, so let's just assume that length of x is smaller than length of pi. And then we can proceed. Okay, so then there is a question, does this have non-empty intersection? And so if E is bigger than C plus 1, then this is indeed the case. Because we will have that Ct of pi x will be bigger than C of x minus 1 plus small o of 1 log length of pi. Okay, so why do we need this additional term here? It's because in the definition of interactive complexity, we concatenate two programs. Sorry, I mean here x, pi, comma x. So this is a simple observation. So there is another question. Can we understand that at least these two sets are computably separable for all n? And so actually there is a program, so we can use symmetry of information of in p-space bounded complexity. But okay, let us...
CI is computable, not? No?
Yeah, CI is computable.
What are the problems then?
Oh, sorry, of course, yeah. No, CI is not, well, CI is computable, but here this one is not computable.
Okay, but what is the problem of computable separation? If one of the sets is computable, then they are separable.
No. Why?
It is not computable.
Why is not computable?
Because we have some uncomputable value in the right hand side.
Sorry, yeah.
Yeah. But still, the p-space program, so if t is a polynomial, then we can solve it in the space t of n.
Solve what?
The promise problem. Y, C, and E. So problem Y, C.
So somehow we can do it not knowing what is complexity of pi. How?
Yeah. And so the program will check conditional complexity, the space-bounded complexity of x given pi. So if it's large, then it will say that it's in NE. And if it's small, it will say, well, it will say not, if it's large, it will say not in YC. And if it's small, it will say not in NE. So this is the idea, but we need a requirement. So if we work out the math, then we need a requirement that E is bigger than C plus 4. So we need E bigger than C plus 1 for the problem to be non-trivial, and bigger than C plus 4 to be like have a solution in p-space. Okay, but that's enough blah blah. Let's finally say what is the main theorem. So then here. So theorem says under small conditions on the parameters, we have that key agreement does not exist if and only if this problem is an IOBBP. So YC T of NE is in IOB. I don't know. I checked my right, but everything was okay. But somehow.
But for which T?
Okay, and so now the parameters. So C should be bigger than 0. No, sorry, bigger than 2, and E minus C. So E should be bigger than C. T should be at least n log n. So big omega, small omega n log n, and polynomially bounded. bounded by n to the power of 1.
So in particular, the right-hand side actually is whatever E and C we have satisfying these conditions, all these things are equivalent, yeah?
Yeah, yeah. Let me write it nicely. N, E. So now at least we have the main theorem. Okay, so there are two directions, and I will prove the easier direction is to use if key agreement does not exist, then we have IOBBP algorithm for this one.
Sorry, now it's written that the condition that E is just larger than C. Is it okay?
Yeah. No, not +4. E, but yeah.
Can you explain? Because you said that just for the problem to be non-trivial, well, I mean, or is it somehow you will show that it's not trivial even if E is just larger than C?
Yeah. So if key agreement does not exist, then indeed it's enough that E is larger than C.
No, but you said that you need that E is greater than C plus 1 to make the set disjoint. And now you say that they will be disjoint. No, of course, if they are not disjoint, this is not in IOBPP.
Yeah. But for E, E equal to C plus 1/2, I don't know if they're disjoint. But still, I know that if key agreement does not exist, then they must be disjoint because it's an IOBPP, infinitely often disjoint.
Strange
but just to understand, so like if Y and N are not disjoint, it means that
it's not an EOBPP. So if they're only disjoint for finitely many lengths, then requirement for IOBPP cannot be satisfied.
Yes. Okay.
Okay, so now my plan, I mean, if you're not too tired, the plan was to prove the right direction.
From left to right.
Yeah. So let us... okay, and so there we will use a Hohenstein theorem.
So you show that if K agreement, so either K agreement exists or these things are in IOBPP. So if they are not in IOBPP, then you suggest some K agreement, yeah?
Yeah. And for this direction, we don't need a lower bound on T. So I could drop it. We only need polynomial upper bound. And so, but I will prove a special case. So I will just prove for C equals 0 and E equals 7. Because then it's easier to, I have to write fewer parameters. So I will remove this and then just choose B. So I will say N 7. Okay, and so I will apply Hohenstein theorem, which says that if key agreement does not exist, so I will abbreviate like this, and if alpha is bigger than beta, bigger than 0, then so every protocol with agreement 1 minus n alpha does not have security 1 minus n to the beta. So every protocol with agreement 1 minus n to the power minus alpha does not have security 1 minus security 1 minus n minus beta.
So alpha is bigger, so agreement is much, error in agreement is much smaller than the security.
Yeah. So that means that we need an if. So it has not security 1 minus n beta. That means that if has to be right with probability 1 minus n beta. So if these assumptions are true, then the protocol can be broken with almost always be broken.
Ah.
So we will have a really strong, powerful if, and we will use them to get our problem y0 and 7 into IOBPP. So that's our plan. And so we will need a strong if only against one single protocol. And so this single protocol is a Levin-style protocol. So the protocol will generate random programs and let them interact and generate secret keys. So it's almost like saying, take a random protocol and run it. And then the same if that breaks this protocol will be enough to solve the, let us define this protocol. And then this if it can guess on input pi, if it can guess x, then we will say that it is not in the n set. So then we think it's in the y set. If if can guess it. If if cannot guess it, then we think it's in the n set. So let me write the protocol. So the problem is that in Hohenstein theorem, we need a good agreement. We need a 1 minus n minus alpha agreement. So we will need to modify our protocol that runs random programs, and we do it by exchanging hashes.
So I'm lost, sorry. Bruno, can you just read what is written here in the statement?
In Hohenstein. Yeah, so if we assume key agreement does not exist, and if alpha and beta are constants, alpha bigger than beta bigger than 0, then for every protocol with agreement 1 minus n to the power minus alpha, so let me write it, it's nicer to see it in a fraction. So if we have very good agreement, but still polynomial, then it does not have security 1 minus beta.
But how can it happen? The first value is larger than the second one.
Yeah. So it must have good, very good agreement. And then we have almost an if that with almost the same probability breaks the code.
Well, wait, if it has good agreement, then do you mean agreement and security? Sorry.
Yeah.
Uh-huh.
Yeah. So the problem is that if a protocol has agreement near 0, then Alice can choose just random bits as key, and then there is no chance Eve can know these keys. So that's why we always have the bound for security will always be lower than the bound for agreement. But we can get polynomially close to the bound of it. Okay. So yes, now let us say what is protocol. So protocol has input n, and what Alice and Bob do is they generate random lengths for programs, and then we should think about the definition of interactive complexity. So they will generate random lengths for programs in interactive complexity and then simulate these programs. So they get some pi and then they get their secret keys. Then they will exchange hashes to increase agreement. And then they check whether it's equal or not. If they're equal, they have their key. If they fail, if the hashes differ, then they output empty string as key. So there is protocol N. And so let me write the 3 steps. So first step, so they generate length of Alice, length of Bob. And so for technical reasons, they will be in between 1 and 3n. So then they generate their programs. A will be a string of length 0, 1 to the power LA. And B will be 0, 1 to the power LB. So then they will run these programs. So they will create a SPI by letting U, A interact with UB. And they generate their keys, X, using V. And so U and V are the same machines in the definition of interactive complexity. So Bob computes V, B, F, Y, pi. So then the next step is that they exchange 5 log n of hash bits. That means that if X differs from Y, they will discover this with probability 1 minus n to the power 5. So Alice sends a randomness S. So Alice sends some random string S. So a hash function, a random hash function with output length 5 log n. And she also sends h of X, h of her key. And then Bob sends, Bob replies whether the hash bits are correct. Bob computes HY and outputs bit just the bits depending on whether h of X equal h of Y. Okay, and that's the finish of the protocol. So now what we prove is that if there exists Eve that breaks this protocol by the conditions of Hohenstein theorem, then this Eve provides us with a solution of the decision problem. So it's what we have to do. So now Eve, we have to say what is our decision algorithm. So the decision decider gets pi and X. And so there will be 2 cases. So it will be given n, length of pi. Because the opponent needs to know some value of n, which will be chosen the length of pi. And it will get pi plus, and then it will put what should be in this protocol here. It will get a hash function, the hash value on X, and the bit 1 saying that the hash values agree. And if this is equal to X, then the output, if this, then answer that we think it is in yes. So we say outside N. And then otherwise, we say outside yes. Okay, so this is our decider for the pair pi x. And so now we need to verify that this is correct. And then we are finished. I know everyone is tired.
No, I think lost, but at least me. I hope that some. I don't want to interrupt you because I hope that someone else can understand what you are saying and can explain it later. But are there some people like this? For example,
Yeah.
Kolya, can you follow? Do you follow and can you explain?
I try to follow. As I understand, we want to construct some key agreement protocol, assuming. So we prove the contrapositive actually.
No. If you are following, let's continue a bit and let Bruno finish. And then it seems that he's saying that he's close to something. And then I will ask you again.
But before, Sasha, Bruno, do I understand correctly that we prove the contrapositive? So we assume that there is a protocol with large agreement that.
So sorry for moving. Yeah. So
that, but which does not have, which has also security, right? And then we construct a key agreement.
Okay, so what we have to prove is that if key agreement does not exist, then why no problem is an IOBBP. And then Holenstein theorem tells us if key agreement does not exist, then every protocol with big agreement can be broken with probability very close to 1.
Okay, and how we prove it?
Okay, so
we are using it without the proof.
Yeah, so I write down one protocol, which is defined, inspired by CY complexity. Its definition is inspired. And then we say, okay, by Holenstein theorem, we have a very powerful if. So if is this, so here there is if, satisfy
but
condition
wait,
of...
Bruno, I don't understand. We use this theorem as given to us.
Holenstein, yeah.
Yeah, I'm not going to prove it. It's difficult theorem. Yeah.
Sasha, I'm lost. I even didn't understand that we do that.
No, but I follow at least, so I would like to try to hear the rest.
Yeah, but it's better to kill all small misunderstandings so that at least 2 people can understand. Okay, so
I
yes.
don't see these 2 people, but let's see.
Yeah. Okay, so now I wrote down protocol. So Sasha, where in the protocol it's not clear. So there are 3 steps. So first step, just select a bunch of random things. So there is 2 lengths, LA, LB bounded by 3n, and then random programs, A and B of length LA and LB. Then we run this program precisely in the same way as definition of interactive complexity. So then we have 2 keys X and Y by this definition. Now we check that they are equal using 5 log n hash bits. So probability, so if X is different from Y, then we fail, the check fails with probability n to the power minus 5 at most. Okay, so that's our protocol. And then if they're equal, then Alice and Bob say that their string is their answer. If they're different, then they output the empty string. Okay, so first everyone agrees that this protocol has agreement 1 minus n to the power minus 5.
I agree.
Yeah, it's because of the hash bits. So if X differs from Y, then they will output the empty string with probability 1 minus n to the power minus 5. So the probability that something goes wrong is n to the power minus 5 at most. Okay, so now we have
should also require that x is at most n bits long, and why? If they are not again, they just output the empty string, I guess. Yeah?
yeah. Okay, good point. Yeah, so I missed this point.
It's a minor thing, but
Yeah. So it's a good remark. So it means that some scale. So let us assume that x has length at most n. So there is some scaling, but it will ruin. So if so this follows if t is close to linear, and otherwise I need to change the parameters here. But I can also change in other places, but I should think a little bit about it. Okay, so let us now assume that that x has length at most. That x length of x is bounded by length of pi. Okay, but then if x is longer than the length of pi, we don't need to prove anything, but still it can happen.
I think you can go ahead.
Yeah.
It's a minor.
Yeah, but okay. So here in the security, we use the length of pi. Yeah, it's pretty dangerous. Okay, let's continue. So now we have to check for IOBPP. There are two conditions. If a pair is in N, then we have to check that the answer is outside Y with high probability. So let us first do the easier one. We check that the pair is in N7. So what does it mean? It means that complexity of pi x is bigger than complexity of pi plus 7 times log of length of pi. Okay? So now let us look to our protocol. It means that if the answer is yes, if the answer is outside N, it means that Eve has guessed X. But the complexity of the pair pi x is much bigger than the complexity of pi. And Eve only knows pi. So how can Eve guess X if X has very big complexity? It must happen with small probability. But we need to be careful. Eve also knows the hash code. The hash function itself is random bits, so it doesn't help. But Eve gets some hint. So we have to check. So what we know is that complexity of, let's say, pi prime. Let's say that pi prime is just all this thing here. What we say is that complexity of pi prime x will be bigger than complexity of pi prime plus 2 log n. To log pi. Why? So when we add h of x, so let me write it in full. Okay, actually for the proof, we don't need to consider this here. What we have here is h and h of x. H of x and the bit 1. So we know that this is equal to c of pi plus okay, so this is what we will prove, that this exceeds So what we need is that this is more than, say, log over pi. And this is true. So this is what we want to prove. And it's true because here we have complexity of pi plus 5. Okay. No, I created a mess. So it's some kind of easy thing. Let me erase it.
So can I just try to understand? So the general idea is that to say that x is small is simple. So I don't know if if outputs x with high probability, then we want to say that x is simple given pi, and then this is a contradiction with being in the null set with this.
Yeah. So sorry, that's what I should say. So let us look to x given pi and h and hx and 1. So here is the protocol that Eve gets. And we want to say that this is large. And so from symmetry of information, we know that C of x given pi is bigger than 7, let's say 6 log n, because it's the easy direction of symmetry of information. Okay, so this is a simple step. This comes just from the assumption that pi x is in N7. So now we apply symmetry of information. So conditional complexity given pi is at least 6 log length of pi. And so this implies that after we add the hash value of x, so h is a random string, it doesn't change the complexity with high probability. And if we add the hash code, it's just 5 log of pi bits. So this can drop the complexity by 5 log pi. And so after this, we still have more than log of pi. And so it means that Eve can never guess x. So Eve will always be in the other place, and it will say outside y. And this is good news because pi of x is in n. Okay, so this is first direction. And now, so the first requirement for IOBBP. Now for second requirement, we will assume pi x is in the yes set. And so the second requirement we prove in the contrapositive. So we will assume, so for the yes set, it means that if algorithm says not in n, then it's indeed not in n. That's what we have to prove. So now second requirement, if d of pi x outputs outside with probability more than 1/3, then pi x is not in n set. So sorry, of course, I mean, if E fails to guess, I wrote it again opposite. Outside y, then it is not in y0. So this is what we have to prove. Okay. So, and then the plan is that, okay, what does it mean? P is outside. So let us look to the construction. So if algorithm says outside Y, it means that E failed to guess. And so what we will say is we will look to the protocol and say that only in very few cases, for very few pi of x, Eve will fail to guess x. Because Eve fails just with small probability. It means that for not too many pairs pi x, it can fail with probability 1/3. And now all these small set of pi x's, they all have small complexity. So we will prove that the condition in Y, we will focus on the right side of the set and say they have very small complexity. But we will check whether they have big interactive complexity. So that's the idea of the proof. So let us define for each L. So let us define a set NL. So we will look to the set of NL of pairs for which we have a problem. So this is the set of pair X where Eve works poorly. So where Eve, so where we have E of length of pi, let us call it pi prime. So the augmented protocol is different from X with probability 1/3. So I didn't use N and L. So I require the length of the protocol to be N. And I require the interactive complexity to be L. So now we will prove that this set is much smaller than 2 to the power L. And this implies, so we will prove that the logarithmic side of S and L is reasonably small compared to L. But by definition, every pi x in the set NL has interactive complexity L. But every pair has complexity much smaller than L by this property. And that means that if pi x is in SL, it's not in Y. Pi x not in Y0. So that's what we have to prove here, what I wrote here. So that's the only thing we need to do is count the elements in S and L. Okay, and so we count the elements, and then from the bound, we will get a bound on the Kolmogorov complexity of the pair. So first, let us bound the size of S and L. So for every pair pi of x, let us check the probability with which this pair pi x is generated by our protocol. So now we have to look back to our protocol. So again, what do we know about S and L? So just the definition. We know that the length of pi is n and that the interactive complexity is L. So I claim that this will, so if pi x is an SL and L, then I claim that in the protocol, we see this pair with probability 2 to the minus L divided by n squared. And 3n squared. To be precise. So let us go back to the protocol. So what do we know? Where is the protocol? Here. So what do we need? Interactive complexity is L. It means that there are programs of length LA and LB with sum equal to L. And the programs A and B produce pi and x. So interactive complexity is L. So this follows interactive complexity. So for such to generate this pair A and B, so to generate the correct programs of interactive complexity, we need that the L's are right, which happen with probability 1 over 3n squared, and the strings programs A and B are right. So note sum of LA and LB is equal to L in this case. So every pi x in the set S and L appears with this probability, 2 to the power minus L, 1 over 9n. Okay. So now we know that Eve fails with high probability when it sees such a pair. It's just by the first requirement in the definition. So now we understand. We know that Eve fails with small probability. So we will apply Ohlenstein theorem with alpha equal 5. And so here we have alpha equal 5 because agreement n to the power minus 5. So let's choose B equal to 4.1, for example. So probability that Eve fails is at least n minus 4.1. And this should be more, so the budget of Eve to fail should be more than size of S and L times the probability for each string, 2 to the power minus L, 1 over 9n. Squared. So what we conclude is that logarithmic size of S and L is smaller than L minus 2.1 log n. So log length of pi. Okay. And now we can bound the complexity of each element in SL. And so here we set pi x in SL. And so here we take pi x in SL. And so we have complexity of x is bounded by, well, we need to tell the two parameters L and N. So that costs us 2 log length of pi plus log size of SL. And so now it nicely works because this log size, so this 2.1 cancels, we have 0.1 left, log length of pi. And so now we should remember what is L. It's just interactive complexity of pi x minus 0.1. Okay, so now we are done. So we can just say that this is strictly smaller than interactive complexity of pi and x. Okay, and so what we have proven is now that pi x is not in Y0. Not in Y0. So now this is precisely what we have to do. And so if d pi x outputs outside Y with probability 1 more than 1/3, so that means Eve is very bad. So that means that pi x is in the set S and L, for L being the interactive complexity, then indeed pi of x, pair pi x is outside Y. So we finished to do this. And so we just wrote down the bad pairs of pi x, the set, and then we show it has small size, and hence every pair has small complexity. And so this is kind of a beautiful argument to finish the forward direction. So I don't know.
Can I try to understand one thing? So the algorithm for this problem that uses the eavesdropper for this protocol. So what exactly happens? So it takes pi, it runs the eavesdropper on pi with a random hash function added, the value of x that it also has, and then it checks whether the output of the eavesdropper, but like on in the last bit, the Bob assumes that what is the last bit of the protocol was what, that the hashes coincide or not?
Yeah, hashes coincide. But of course, eavesdropper doesn't care what is the value of y and so on. He just adds 1 just to simulate the protocol.
So we always, in the algorithm for this problem, promise problem, we always run it on a like on a transcript where in the end, like it's supposed to be that the hashes coincide.
Yeah. So this is not correct, but still this last bit is wrong with very small probability. So it doesn't really affect the probability.
Well, so, I mean,
so you say, so your complaint is that the distribution are not exactly the same when E is run. So E is run on a different distribution. But how much this distribution is different? So it's different because in the distribution to which E is applied, the last bit is always 1. And you say, oh no, but in this protocol, it can happen that bit is not 1. Oh, sorry, but sorry. On those inputs from S, it's always 1.
Because it's by the definition of the interactive complexity that they produce equal strings.
Yeah. Sorry, yeah. Yeah, so sorry. So this pair programs AB is guessed with a given probability, and for these programs, the protocol always produces 1 in the end. Because by assumption, we assume that A and B produce same key for Alice and Bob.
Okay, so is there anyone who can explain later, now it's too late probably, but can explain what happened? Maybe in 2 weeks from now, someone, for example, Kolya, will explain what Bruno was saying.
Yeah, I can explain it again. I understand that the writing was slow.
No, actually, there are many ideas that we need to grasp. So first there is idea of kind of what this interactive complexity, and it's kind of nice notion which should be understood. The role of X is especially important, I guess.
Yeah, actually, I changed it from the original paper by Mazor, Bauwens, and so on. They have pi xy, where x is generated by Alice and y generated by...
No problem. It's even better if you have smaller set of things. And then there is another idea somehow of stability of and amplification. It seems that you kind of use the simplification tools to do something. Maybe I guess this Hollenstein theorem is kind of amplification thing also.
Yeah. So it's actually boosting algorithm from machine learning.
Okay, maybe we should try to study separately the things to understand them better. So Kolya, are you prepared to give a long crash course on these topics? I think you are in the best position.
Sasha, I've been lost to understand how the Hohenstein theorem implies.
So Hohenstein gives us very powerful Eve.
Yeah.
Okay,
even
I
if the
think
protocol
now it's no chance to explain everything from the beginning, but still you can.
I can just listen.
And also maybe
trying to understand.
It doesn't look likely, but maybe reading the paper you can understand something.
Yeah, it's unlikely.
We are quite pessimistic, but still we should give it a try.
But anyway, this is not for the next session.
Not for the next time, because next time we have this universal machine universality. By the way, I think if the speaker should make special effort to invite Peter Gach, because he's mentioned in this announcement, and it would be nice, since we have it from time to time, it would be nice to have him next time. So you can suggest a speaker to contact Peter.
Okay, so but anyway, tomorrow I will write, polish my note and send it to the mailing list so everyone has it.
Yeah. No, if you do it not tomorrow, but the day after tomorrow, we will not be very disappointed. So
okay.
No, it's very interesting topic, but it is just too fast for us. We need to go not to rush to some specific point, but we want to understand more around and what is easy things, and before getting to non-trivial things.
Yeah, but I'm also not happy about my explanations.
Okay. Let's.
Bruno, but you only showed half of it, yes?
What about the other direction?
The other direction.
This is self-contained. So
Bruno's innovation is in the other direction. This one is pretty much from the paper.
So it's a little bit harder, but it's self-contained. I mean, there is hash over left lemma in the last version.
Yeah.
So this version was 2 pages in the note, but we also had the statement of the problem, which is 2 pages, and then the other direction is 3 pages. So it's less space than what we did today. So it should go faster.
It's not.
Not a directed connection.
I don't know. Maybe some of us are more advanced, but for me it was completely. Everything was completely strange, but let's.
Yeah, but just in the last 10 years, there are some nice applications
of
Kolmogorov complexity.
We should follow this new development, and this is one of the very.
And also here, Hara stuff, we should, the connection between symmetry of information and one-way functions.
Okay.
So we should catch up. Okay.
Yeah. No, thank you, and I still hope for Kolya's explanation in 2 weeks. But
okay,
we have also other possible talks probably, but still, if it's
no hurry, Okay, nice to see you. Thank you for all attention. Bye.
Bye.
Thank you.